Hi everyone, I am Sujani, faculty in physics at Institute of Aeronautical Engineering, Hyderabad. Today we are going to see some numericals based on Hall effect. So before doing the numericals, let us have a quick recap of the formulae that we are going to use. So the first one that we are going to use is RH is equal to 1 upon Ne. So if I am talking about electrons as the charge carriers, we have RH is equal to minus 1 upon Ne. And if it is due to holes, we have RH is equal to 1 upon Pe. RH here represents the Hall coefficient. N represents the electron concentration. P represents the hole concentration. And E is the charge of the electron. Now the second formula we have here is to calculate the value of RH using the Hall voltage. So VH into T upon B into I. RH is equal to VH into T upon B into I. RH is the Hall coefficient. VH here denotes the Hall voltage. VH is Hall voltage. Small t here represents the thickness of the specimen or the semiconductor. B here is the magnetic field, or we call it as magnetic field induction. And I is the current. I is the current. Then we are also going to calculate sigma. Sigma is the conductivity. Sigma is equal to N E mu E plus mu P. If we are writing a general expression for sigma, we write N E mu. But here in a semiconductor where we are seeing it is due to electrons as well as holes. Of course, if it is N-type, the electrons are the majority carriers. But we are considering the mobility of the electrons as well as the mobility of the holes. So we write here sigma is equal to Ne into mu E plus mu P. What does sigma denote? Sigma is the conductivity. N here we have already defined electron concentration. E also we have defined charge of the electron. And mu represents the mobility. Mu is the mobility. And this suffix represents if it is E, electron. If it is P, it is due to holes. Then from the same formula, if we have to calculate the mobility, mu will be equal to sigma upon Ne. Because we want to find mu. So mu, we can take Ne onto the other side. So mu is equal to sigma upon Ne. Suppose N and E are not given. We know the Hall coefficient and we know RH is equal to 1 upon Ne. We can write it as RH into sigma. We can calculate mu knowing the values of conductivity and Hall coefficient also. And one more formula is, if you know the conductivity, you can find the resistivity. So rho is the resistivity you can get using 1 by conductivity. Here rho represents the resistivity. So all these formula will be very handy. They are very simple formula, and the numericals we are going to do are also very simple. But when you are applying the formula and calculating the value, your concept will become very clear. So that is why you need to do a number of numericals with different data so that your concept becomes very clear. So I hope with these formulae we will move forward with doing the numericals. So first one, electron mobility and hole mobility in silicon are 0.135 meter square per volt second and 0.048 meter square per volt second respectively at room temperature. So we are given the mobilities at room temperature, and the carrier concentration is 1.5 into 10 power 16 per meter cube. We have to calculate the resistivity. Exactly the same, only thing is the values are changing here for mobility and concentration. So what is the data? The concentration, the carrier concentration is given. N is equal to 1.5 into 10 power 16 is the concentration. Then we are given the mobility. Electron mobility is 0.135 and hole mobility mu h is 0.048. We also need the value of E, so I write E is equal to 1.6 into 10 power minus 19 coulomb. We have to find the resistivity, rho. So use the formula now. Sigma is equal to Ne into mu E plus mu H. So sigma is equal to, substitute for N first. 1.5 into 10 power 16. For E, 1.6 into 10 power minus 19. Then mu E plus mu H, 0.135 plus 0.048. So you simplify, you get 0.4392 into 10 power minus 3 per ohm meter. Now to calculate the resistivity, what we do, resistivity is 1 upon conductivity. So 1 upon 0.4392 into 10 power minus 3. So we get 2.2768 into 10 power 3 ohm meter. So this is the value of resistivity. Next one. Evaluate the value of carrier concentration if RH of the specimen is given 3.66 into 10 power minus 4 meter cube per coulomb. So it's a very simple numerical. What is the data given? RH. RH is 3.66 into 10 power minus 4. We have to find carrier concentration N. We know the value of E, 1.6 into 10 power minus 19 coulomb. So how do we get the value of N? What is the formula? N is equal to 1 upon RH into E. Because we know the value of RH, we know E. So we write N is equal to 1 upon RH into E. So 1 upon RH value is 3.66 into 10 power minus 4 into E is 1.6 into 10 power minus 19. Just simplify, we get 1.708 into 10 power 22 atoms per meter cube. So knowing the value of RH, you can easily calculate the value of N. The next problem is on Hall effect. A silicon plate of thickness 1 millimeter, breadth 10 millimeter and length 100 millimeter is placed in a magnetic field of 0.5 Weber per meter square acting perpendicular to its thickness. If 10 power minus 2 ampere current flows along its length, obtain the Hall voltage developed if the Hall coefficient is 3.66 into 10 power minus 4 meter cube per coulomb. So we are given the magnetic field 0.5 Weber per meter square. We are given the current 10 power minus 2 ampere. Given the Hall coefficient 3.66 into 10 power minus 4. And what it is mentioned here is the current flows along the length. So this also we should know. If the current flows along the length, along the breadth, we apply the magnetic field. So a Hall voltage will be developed along the thickness. Because here they have given all the dimensions. The length is given, breadth is given and thickness is given. So whatever data that is required, we will write first. So in the solution, first we'll write the data. B is equal to 0.5 Weber per meter square. Magnetic field is given, B. Then we have the current. I is equal to 10 power minus 2 ampere. Current is given. And Hall coefficient is also given. RH is equal to 3.66 into 10 power minus 4. Hall coefficient is also given. And now the Hall voltage is developed along the thickness. T is equal to 1 millimeter. So we will do the conversion here. All the other units are in SI system. Weber per meter square, ampere, meter cube per coulomb. All are in SI. So we need to write this thickness also in SI. So this will be 1 into 10 power minus 3 meter. And what we have to calculate is the Hall voltage. VH is equal to how much? So we'll use the formula. RH is equal to VH into T upon B into I. We want to find VH. So RH into BI upon T. So actually you can remember the formula for voltage also. But it is always better to remember the standard formula and write the appropriate. Otherwise, in examination, you may have confusion regarding what is there in the numerator and what is there in the denominator. So I am always using the standard formula RH. One formula I will remember. So from here I can deduce VH, I can deduce T, B, E, I. Any formula I can write from here. So I am remembering only one basic formula RH. So VH is equal to RH into BI upon T. So let us substitute. RH is 3.66 into 10 power minus 4. B is 0.5. I is 10 power minus 2. And thickness is 10 power minus 3. So if you simplify, what we get is 1.83 into 10 power minus 3 volts. So when you substitute and simplify using your calc, you will get 3.66 into 0.5. So when this minus 3 goes to the numerator, it will be plus 3. Minus 4 and minus 2 is minus 6 and plus 3 you get minus 3, 10 power minus 3. So 10 power minus 3 we can also write it as millivolt. So I can simply write it as millivolt. answer can also be written as millivolts because it is 10 power minus 3. 1 volt is equal to 10 power 3 millivolts. Next one. The Hall coefficient of a certain silicon specimen was found to be minus 7.35 into 10 power minus 5 meter cube per coulomb from 100 to 400 Kelvin. Means this is the temperature range. Determine the nature of the semiconductor. You have to talk about the nature of the semiconductor. And if the conductivity is found to be 200 per ohm meter, calculate the density, that is the charge carrier density, and the mobility of the charge carrier. So we are given the Hall coefficient, that is minus 7.35 into 10 power minus 5. Okay, so let us write the data. RH is minus 7.35 into 10 power minus 5 meter cube per coulomb. And then we are also given the conductivity. Sigma is equal to 200 per ohm meter. You need to calculate the charge carrier density N and mobility mu. And also we have to find mu also. Now, first thing they are asking about the nature of the semiconductor, means what type of semiconductor it is. If the value of RH is negative, so RH is negative. So this implies that it is an N-type semiconductor. So that is what is asked. Nature of the semiconductor means it is an N-type semiconductor and the majority carriers are electrons. So the current here is due to the electrons. Majority is electrons. So that is what we are talking about, the nature of the semiconductor. Then we will calculate the density. So formula we'll use now for density, charge carrier density. N is equal to 1 upon RH into E. So again the same way for Ni we have minus 1 by RH into E. So N is equal to minus 1 upon the value of RH is minus 7.35 into 10 power minus 5 into E is 1.6 into 10 power minus 90. So this minus will get cancelled. So we will get N is equal to 8.455 into 10 power 22. Atoms or charges or electrons per meter cube. So this is the value of N we have got. Now calculate the mobility. So once we get N and we also know RH, we can simply find the value of mobility, mu. We have to find, we need to find the value of mu. So mu is equal to sigma upon Ne, or we can write sigma into RH. So sigma is 200 and RH is 7.35 into 10 power minus 1. So for mobility, we need not consider the charge because they do not have the direction. We are only talking about how they are moving, mobility. So 0.0147 meters square per volt second. So since we know the value of sigma and RH both, I am substituting directly. 200 into 7.35 into 10 power minus 5, we get 0.0147 meters square per volt second. Now the next one. In a p-type germanium, Ni is equal to 2.1 into 10 power 19 per meter cube. Then density of boron is 4.5 into 10 power 23 atoms per meter cube. The electron and hole mobility are 0.4 and 0.2 meter square per volt second. So what is its conductivity before and after addition of boron atoms? So you need to first understand the question and then we will try to do it. Now the concentration is given here. Ni is 2.1 into 10 power 19 per meter cube. So to that what we are doing, we are adding an impurity. We are adding a trivalent impurity, boron. Boron is a trivalent impurity. How many atoms we are adding? 4.5 into 10 power 23 per meter cube. What we are supposed to find? We have to find the conductivity before and after addition of boron atoms. Means before addition, what is the mobility? And after addition, what is the mobility? That is what we have to find. So first write the data. Ni is given 2.1 into 10 power 90. We need the mobility for electron 0.4, for hole 0.2. Let us write the units also per meter cube. This is per. We have to find the conductivity, sigma. Now the density of boron atoms, Nb I will write, density of boron atoms, 4.5 into 10 to the power of 23 atoms per meter cube. We have to find the conductivity before and after. First we will find for sigma before. So what is the formula? We have Ne into mu E plus mu H, because before adding the trivalent impurity, the conductivity is due to both electrons as well as holes, and we know the mobility of electron and holes. So we will use the formula for sigma, that is before addition of boron atoms, Ne into mu E plus mu H. So what is the value of N given? 2.1 into 10 power 19. The value of E 1.6 into 10 power minus 19. And mu E plus mu H is 0.4 plus 0.2. 10 power plus 19 minus 19 will get cancelled. So 2.1 into 1.6 into 0.6. This will give us 2.016 per ohm. This is the conductivity before. Now, how do we calculate the conductivity after adding the boron atoms, that is after adding the trivalent impurity? So now the concentration of boron atoms, I'll write it as P. Nb, or this is simply P. We can also write it as P. Is 4.5 into 10 power 23. Now, how will this formula for conductivity get modified? Sigma after will be Pe into mu H. Hope you understand the formula, because it is now due to holes. I consider the concentration of atoms of boron as P into E into mu H is the mobility of hole. So what is the value of P? 4.5 into 10 power 23 into 1.6 into 10 power minus 19 into mobility of hole is 0.2. So this will give us 14400 per ohm. So the value of conductivity before adding the boron atoms is 2.016, but after adding boron atom it becomes 14400. So your concept of adding an impurity, that is doping, also has to be clear with this. So on adding an impurity, we are trying to make it more conducting. So the conductivity increases. It means it conducts more. So you need to apply and relate to the theory. What we have seen in the theory in N-type and P-type is on addition of an impurity, what are the changes that are happening in mobility as well as in conductivity. Next one. In an N-type semiconductor, it has a Hall coefficient of minus 4.16 into 10 power minus 4 meter cube per coulomb, and the conductivity is 108 per ohm meter. Calculate the charge carrier density and also the electron mobility at room temperature. So let us write the data. N is equal to, we'll have to find the value of N, calculate the value of charge carrier density. Given is the Hall coefficient. Hall coefficient RH is minus 4.16 into 10 power minus 4. Conductivity sigma is 108 per ohm meter. What is the carrier density and what is the mobility? These two you have to find. So the formula, first to find N. So N will be equal to 1 upon RH into E. E is equal to 1.6 into 10 power minus 19 coulomb. E is equal to 1.6 into 10 power minus 19 coulomb. So let us just substitute for N. N is equal to 1 upon RH. What is the value of RH? 4.16 into 10 power minus 4 into the value of E, 1.6 into 10 power minus 19. So when we simplify, you can take 10 power minus 4 and 10 power minus 19 is 10 power minus 23. So 10 power 23 upon 4.16 into 1.6. We get 1.502 into 10 power 22 atoms per meter cube. This is the concentration or the carrier density, charge carrier density. Next, we need to calculate the mobility. So, what is the formula for mobility? Mu is equal to sigma upon Ne or sigma RH. So, we'll use the second one because we know both sigma as well as RH. Sigma here is 108. RH is 4.16 into 10 power minus 4. So we get 0.045 meter square per whole second. So we are getting the mobility as well as the carrier, charge carrier density. One more similar problem. In an N-type semiconductor, the concentration of electron is 2 into 10 power 22 per meter cube. Its electrical conductivity is 112 per ohm meter. Calculate the mobility. In this case, we are given the concentration. In the previous case, we were given the Hall coefficient. So let us write the data. The concentration is N is equal to 2 into 10 power 22 and the electrical conductivity sigma is 112 per ohm meter. You need to calculate the mobility mu. The value of E is constant 1.6 into 10 power minus 19 coulomb. So what is the formula we are going to use? sigma is equal to NE mu E or NE into mu. The general formula we use is NE into mu. So the mobility mu will be equal to sigma upon NE. So let us just substitute. What is the value of sigma given? 112 per ohm meter. So 112 upon the concentration NE is 2 into 10 power 22 into E. The value of E is 1.6 into 10 power minus 19. So simplify, we get mu is equal to 0.035 meter square per volt second. So this is the mobility we are getting given the value of N and sigma, that is charge carrier density and conductivity. One more numerical we will do. A semiconducting crystal with 12 millimeter long, 5 millimeter wide and 1 millimeter thick has a magnetic density of 0.5 Weber per meter square and applied from front to back perpendicular to the largest faces. Means the magnetic field is applied from front to back perpendicular to the largest faces. Now when a current of 20 milliampere flows lengthwise, so the current of 20 milliampere is flowing along the length and the voltage measured across its width is 37 microvolt. Mu V here represents microvolt. So what is the Hall coefficient of this semiconductor? So let us write the data. We have a magnetic field B is equal to 0.5 Weber per meter square. That is the magnetic field that is applied from front to back perpendicular to the largest faces. And then the current is given. Current is 20 milliampere. Again here we need to convert this milliampere to ampere to be in the same system. Throughout we are writing it in SI system. So 20 milliampere we will write it as 20 into 10 power minus 3 ampere. And then the voltage measured across its width is found to be 37 microvolt. So what is the voltage? VH 37 microvolt. So we will write it as 37 into 10 power minus 6. Micro here is 10 power minus 6. So 10 power minus 6 volt. We have to find the Hall coefficient. RH is equal to what? And the thickness here is what? 12 millimeter long, 5 millimeter wide and 1 millimeter thick. So the thickness here is 1 millimeter. And we will write it in meter as 10 power minus 3 meter. So let us write the formula. RH is equal to VH into T upon B into I. So RH is equal to, what is the value of VH? 37 into 10 power minus 6 after converting it into volts. And the thickness in meter is 10 power minus 3 upon the magnetic field is 0.5 and the current is 20 milliampere. So we can simply write RH is equal to, you have 10 power minus 3, 10 power minus 3 will get cancelled. 20 into 0.5 you will have 10. So 37 divided by 10 into 10 power minus 6. This is 3.7 into 10 power minus 6 meter cube per coulomb. So this is the value of RH. So you may use your calc directly, or wherever you can do the simplification, you can do the simplification and write the values. But identifying the data, writing the data correctly, applying the right formula is very important. Thank you. We'll see you again with more numericals in the next lecture. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.